So today we are going to discuss the what happens next kind of like situation with convex optimization, mixed integer part. So we covered what you can reasonably call the entirety of classical convex programming. You can, I repeat it every time, so probably no harm in repeating it one more time. So we started with what I would say is not even convex optimization, but linear algebra, so least squares. Then we went into our, LP, QP, SOCP, together with QCQP. It's kind of like they're kind of the same. People don't treat them separately. You don't have separate solvers for QCQP. And then SDP, okay? And this is more or less the entirety of modern convex optimization. There are plenty of things that you can do with those. For example, like today, before class, before the recording, so we had a question about sum of squares. Sum of squares would be somewhere here with SDP. So you remember we studied before that something like Chebyshev center of polytope that was with LPs. We can discuss, for example, MPC, that would be with QP. Etc. So plenty of applications for those things. But basically, what happens is remember minimum covering ellipsoids, SDP, maximum inscribed ellipsoids, SDP, LMI control theory, SDP, etc. All of this is kind of like applications of the same basic structures. And what distinguishes those guys is basically the solvers, right? Like here you can just use pin or the least squares. For LP, you can use LP solvers or anything higher than LP. For QP, you can use QP solvers higher than QP. For SOCP, you can use various SOCP solvers, right? For SDP, you use SDP solvers, right? And of course, SDP covers everything from below, SOCP everything from below, QP, etc. Right? Good. And just as a reminder, for example, the pinf is the implemented function Python and MATLAB is everywhere. LP would be implemented as, for example, linprog in MATLAB is going to be everywhere implemented. It's a very powerful tool, not going to break for millions of variables often. It depends, of course, on your implementation, but it is very powerful. QP, MATLAB implementation, for example, quadprog, easily handles thousands of variables with no issues whatsoever. Extremely powerful. SOCP, like something like Sadumi, has been a very popular free solver. Mazek and Gurobi, popular commercial solvers, provide you ways to solve SOCP. SDP is also provided. I think Gurobi provides it, but I can be wrong. But I can be wrong. One of the Gurobi or Mazek provides you. SDP3 is a very popular solver. I hope I pronounced the name correctly, for SDP. So basically, we have this kind of realm where we have problems and we have solvers for them, okay? And when people talk about convex optimization, they basically talk about this part, right? But that is not all that people use in this realm. So this is maybe what they mean when they say convex optimization, but there is more. And so the next part is mixed integer. I'll put it here, mixed integer. It is no longer convex. So that is one thing you have to kind of like keep in your mind. mixed integer is not convex. So while we're going to talk about it, it is not part of convex optimization. It's okay. Our course is not limited to convex optimization. Remember, we studied linear algebra, and we're now going to stick out and study something that is more of a general nonlinear optimization, right? But it is intimately related to convex optimization. It uses convex optimization tools, and usually the same people who are interested in convex optimization use mixed integer. So there's intimate relation between the two. All right. So that is just for you to kind of like understand the picture, understand what's going on. We went through the classical convex optimization. Of course, there are more convex optimization programs, and you could even generalize over SDP. SDP is not most general form of convex program. But that is all that people use in practice, as in that is popular stuff. Now we are going beyond this popular stuff. We are going to what is for sure not a convex program. All right. So now let us try to understand why we go there. Why? Right. So let's look at the general form of what mixed integer is. So mixed integer is a problem with, let's say, linear cost, decision variable x, inequality constraints, equality constraints. So this is a general form. When I say a general form, sorry, mixed integer linear program. That is why we have linear cost, linear inequalities, linear equalities. So there's a linear mixed integer linear. Okay. All right. So far, if you look at this part here that I just highlighted, this is just LP. It is just linear program. What makes it mixed integer is the fact that some of the variables are real and some of the variables are integer. That is the difference. That is what makes it different from that's what makes it different from classical. Yes. Okay, probably not the question. All right. So this is what makes it different from LP. The fact that some of the variables are integers. So let me just draw your attention to it one more time. This is the difference. Some of the variables are integers. What does it mean for the variable to be integer? Well, it means that it can only assume whole values, like integer values. X sub n, for example, can be 3, 4, 5, minus 2. It cannot be 0.5 or 1.3. It can only be a whole number. Okay. That is the whole idea of what makes mixed integer programs different from normal ones. Some of the variables are restricted to be only whole numbers, integer numbers. Now, let us try to understand if it is convex or not convex. Can someone tell me what you think about its convexity? And with argumentation. Okay. Is it convex or not convex, this optimization form? Let's think about its domain. What is the domain of this problem? Well, the way I ask this question is probably a little bit hard to answer, so let me just start. So for, let's say, integer variable, let's say we have only two integer variables. Let me try to do it this way. Let's say we have only x1 and x2. X2 is, let's say, mixed integer variable. Let's say that this is the situation that we are working with. So let's say we have two variables. So for x1, the domain would look just normal. Like domain for x1 is all R, and unless the inequalities here do something. If inequality, but if we don't have any inequalities, then the domain is just R. So this would be the domain for x1. See. Yeah, I don't even need a second line, right? It will be just so difficult to draw in Zoom. Sorry about that. It will be just here is 0.0. Here's 0.0. Right. And the entirety of this domain would be for x1 would be admissible. So we could denote it like this. This whole thing is the domain. Okay. Good. Now, what about x2? What about x2? For x2, it is only integer variables. So it is, let's say, 1, 2, 3, 4, etc. So, or if we want to be a little bit less crazy. Yeah. So anyway, 1 would be 1, 2, 3, 4. So this is number 1. This is number 2. Number 3. This is x2. All right. So this is the domain. With those vertical spikes, by them I meant that it is just x1 is defined at a point. I guess, yeah, I could even draw this. If this is x1, this axis, vertical axis is x1, then we can. Then it is this is actually the domain of the problem. Yeah, maybe this is like better somehow. Can get rid of this part. So this will be the domain of the problem. Okay. This is the domain of the problem. So vertical axis x1, x1 can go anywhere from -infinity to +infinity, but let's keep it positive just for simplicity. And x2 can only assume integer variables. So this is the domain. Now, how can we prove that it is not convex? Someone tell me. How do we prove that it is not convex? Anyone?
Actually, we can find a line
Yeah.
between 3 and 4, which is not in the domain.
Yeah, exactly. That's all you need to say, right? You find a line between 2 points. 2 points are in the domain. The line itself goes outside the domain, so it's not convex. Exactly. Good, great. So we already proved that this problem is not convex. Okay, good. So this is what's going on in this situation. We have a non-convex domain. Right. Good. Now let's just move a little bit further. We'll look a little bit more on general formulations, and then we'll see what's going on. So more general form would be something like this. You have a cost, which is convex in decision variables. So the cost itself has to be a convex function if you're going to minimize it, concave if you're going to maximize it. You have some sort of inequality. Here I have written it as a linear inequality, but you can imagine here it can be, you know, like, I didn't write as linear inequality, but how should I put it? What I mean is it can be linear, can be SOCP, so second order cone, SOC, second order cone, like with the norm, can be even SDP, can be quadratic. So it can be any of those that are admissible in convex programming. We can do any of those. Yeah. So, but as long as it is convex, and it is one of those recognized ones, we have, as usual, linear equalities. Equalities, as you probably noticed, always linear. We don't get to have equalities which are anything but linear. And it makes sense, remember why, because this is only thing that is both convex, concave, right, linear functions. And somehow introducing linear inequalities does not lose convexity, whereas anything else would. Right. And we have some variables that are continuous, sometimes some variables that are integer. Good. So this is the whole thing. The problem is completely as usual. Let me do it. Completely as usual until here, and strange here. So this is a novelty. This is a novelty. Let us see how we can work with it. So first, let us just spend some time appreciating the strangeness and properties of this. So first of all, mixed integer problems are not convex, as we said. But the name somehow has a convexity there. Okay, so what this stands for, this convex in the name, what it means is that if the values of the integer variables are either decided, so you fix them, you say, okay, this is no longer a variable, this is now a constant, the problem then will become convex. That is one thing. Another, if you relax them, if you allow those mixed integer variables to become continuous variables, it will also become convex. So the problem has to be convex in both situations, whether the variables become constants or if they are relaxed to become continuous variables. Which is, by the way, if the problem is convex when the variables are continuous, from this, by definition, it means that it would also remain convex if you fix something. So that is the second implies the first. Okay, so it is convex in the sense that a mixed integer part, like the integer variables, is the only thing that separates it from being a typical convex problem. Okay. Why is this important? Why is it important that it is convex? Why it is important that only mixed integer variables are standing in the way of it being a convex program? Well, there is a good reason. It is because we usually use branch and bound algorithms to solve those. And those algorithms take advantage of the fact that if you fix integer variables, you get a convex problem which can be solved very easily. And not even just easily, but also with the existing algorithms. So those branch and bound algorithms, they take advantage of the existing methods for solving convex problems. That is the first. Second, they take advantage of the fact that you can relax mixed integer variables to obtain approximation of the optimal values. So you cannot just replace mixed integer variables with something else and get a solution. But you can relax them and get an approximation of the solution. We will see it in a bit. So that is the point. It is not just like any nonlinear optimization where things can be as bad as you can imagine. Instead, it is a quite reasonable, how should I put it? Kind of like extra step that you make. You solve essentially a convex problem, but with one additional, nuance. Some of the variables have to be mixed integer. But since we know a lot about how to solve convex problems, we take advantage of this knowledge. Since we know a lot about how the problem will behave if we pretend like the variables are not integer but continuous, we can also use this knowledge to approximate. So somehow those factors allow us to solve this problem. Okay. Don't mistake mixed integer problem for general non-linear optimization. They are quite different in behavior. All right, good. But in the worst case scenario, mixed integer will perform exhaustive search. Okay. In worst case scenario, it will perform exhaustive search. So in worst case scenario, it will be just trying all the possible values of integer variables until it succeeds to find the best one. So convex optimization is guaranteed to converge with some speed. And we didn't study it yet, but if we have time for it, I will show you how it works. When it approaches the vicinity of the solution, quadratic program, for example, converges with the double the precision on each step. So the precision of the solution, it adds 2 digits to the precision on each step. So the precision just goes up extremely fast, and you can just stop iterating in like 3 or 4 steps when you are close enough to the solution. That is extremely powerful result, allowing you to control your precision of your solution. Of course, that is in the vicinity of the solution, but still. None such luck in mixed integer. You don't have guarantees. Worst case scenario, you can just try all possible combinations of your integer variables until the sun sets, and even then it might not be done. So there is no guarantees, and that is part of it being non-convex. Only convex problems have nice guarantees, but usually it does solve fast enough. That is the situation. Okay, now in robotics applications, mixed integer variables are often replaced with binary variables. So we often only discuss variables which are either 0 or 1. We don't discuss mixed integer variables, we discuss binary variables. And that is extremely typical. We still call it mixed integer, but it is actually mixed binary. Okay. Mixed binary. So very, very, very popular thing in robotics. And in robotics specifically, we don't use integer variables, we use binary variables. Okay. And of course, in your solver, you would have to check what kind of variable your solver provides, integer or binary. Branch and bound algorithms for binary variables naturally have easier time because each node would only have 2 branches. What can x1 be? 0 or 1. What can x2 be? 0 or 1. What can x3 be? 0 or 1. Right. So if you think about it, if you have 10 variables, you can already know how many possibilities you have. 2 to the power of 10. Right. It's kind of like right. Am I correct? 2 to the power of 10, I think. It is the number of vertices of the hypercube in this like dimension, in the dimension space of the variables, because it can only be like 0 or 1. So it's equivalent to being vertices of the cube with a side of 1. All right. Now this is the situation here. Do you have questions for now? I'll go into the examples after the slide, so we will see more. But do you have questions for now? Okay. So let us go into one like main example, I guess, that I want to show you. And the main example will be footstep planning. footstep playing. That example is instantly a little bit on the complicated side, but that is the primary use of, I mean, not primary, but like a very typical use of mixed integer variables in robotics. So I'll just start with that. So given n convex regions represented by linear inequalities, so H representation, okay, find a sequence of k points, footsteps, from a given starting point to a given goal point, such that all footsteps lie in one of the convex regions. You can think about it as path planning, but just discrete, okay? Just discrete. If those regions intersect, you can have a continuous path. If they don't intersect, you cannot have a continuous path. So it's, the situation. If they intersect, you can think of it as applying a path for a vehicle. If they don't intersect, you can think of it as applying a path for a walking robot, for example. If they are 3D, you could think of it intersect. You can think of it as applying a path for a drone. So all of those, and all of those are where you use this actually. So it's not made up. That is, people use it for those applications. Less for vehicles, but that is a separate story. All right. So which let me try to use again Zoom to illustrate how it's done, what we are talking about here. So we have regions. This is, let's say, one region. And I guess let me do colored regions. Okay, so this is one region. And this is another region. And let's say maybe here's the final one. Question is, how do you plan a path? I'll denote it by red dots that goes from the initial point. Let's say initial point is blue dot here to the end point, which is a green dot here. You want to plan a discrete sequence of steps. So something like a step here, step here, step here, step here, step here, and so on. So you want to plan a discrete number of steps that would go from the beginning to the end. And each step has to be inside at least one of the regions. So for example, what is not allowed is to have, let's say, a step here. This would not be allowed. So this would be unacceptable. How do you do that? You know how to check that this particular step, let's say we denote it as xi, you know how to check that xi is inside particular region. So let's say inside the region number 1, it will be a times xi less than b. Okay, if this is a b region. Okay, so if this a1 b1, then it will be a1 times xi less than equal to b1. Okay, so you know how to check this condition, but you don't know how to check the conditions that it has to lie at least in one of the regions. So what you want to say is it should be either a1 times xi less than equal to b1, or x2 times xi less than equal to b2, or x3 equals to times xi less than equal to b3. So you have like or in your optimization. Or is not a part of optimization. We don't have or in optimization. There's no or. So we have only and. So all our conditions have to be achieved simultaneously. We don't have or. So somehow we have this problem where we need to make sure that those points lie inside the regions. But how do we do that? How do we achieve this situation? Now, let me just, before we go, let me comment on the cost function. Here I say that the first point should be as close to the start as possible. Here I said that the last point has to be as close to the goal point as possible. We could also add additional cost on the distance between sequential steps. So the steps would be kind of like equally spaced. That is very typical constraint, very typical cost. Yeah, so that is the, and that is the decision variables here. Right, so what do we do? What do we do? How do we do it? So this is where mixed integer comes in. Well, let me show you how it's done. So one of the key methods associated with the use of mixed integer programming in robotics is the big M method. Big M is stands for using big constant named M. This is one of those methods which where the name is just great, and it is also very silly. So it's like a really good name, very silly too. So hopefully you will remember it. Okay. Assume you have two inequalities, a1x less than b1 and a2x less than b2. Okay, two inequalities. We'll be happy if at least one of the two holds. Okay, at least one of the two have to hold. So we introduce our binary variables, C1 and C2. They're binary, so they can be either 0 or 1. They cannot be anything else. Can only be 0 or 1. Okay. And we introduce a big constant M. That is where big M comes from. We introduce big constant, like let's say 100, named M. The name is not necessary, but that's how we usually call it. So big M's, you know. All right, big constant named M. And we choose it so big that a1 times x less than or equal to b1 plus m would always be true for any admissible x. So whatever x you choose in your space of a possible x, usually x is not expected to be like billions, right? In all reasonable problems, x is within some bounds. Those bounds are not necessarily stated explicitly, but even in our path planning problem, you can imagine no path would deviate from the origin more than, let's say, 100 meters. So there is always such limitations on x, implicit or explicit. Right, so we choose m in such a way that this would always hold, and that this would also always hold. Notice that this is just a scalar. This is a scalar. This is a scalar. Same here. So let's say you have a1 times x less than or equal to -1 plus 100. So instead of -1 here, we have 99. And if a1 times x is less than or equal to 99 for all possible x, yeah, good. We're done. Same here. So that's how we choose m, to make sure that both of those always hold. Then, if we did it this way, we could rewrite our problem in the following fashion. We say, okay, let us have ax less than or equal to b1 plus m times c1. Okay, m times c1. And same for the second constraint, a2x less than or equal to b2 plus m times c2. Okay, c can be 0 or 1. If it is 0, then this whole part will go to 0. If it is 1, then this constraint will always hold because of this reason. Because of this. Right? We chose M so big that it will always hold if C is 1. And there are only two options. If C is 1, it always holds for the same reason. Okay. If C is 0, then this guy goes away. Okay. Now, last touch. We make sure that C1 plus C2 is equal to 1. Now we have essentially two options. Originally, you could say we have 4 options. One option, like if we get rid of this constraint, we had 4 options. It would be C1, C2 equal to 0, 0, C1, C2 equal to 1, 0, 0, 1, and 1, 1. Okay. But because of this constraint, we only have now 2 options. And which are those options? Well, it is C1 equal to 0, C2 equal to 1, and C1 equal to 1, C2 equal to 0. Only 2 options are available now. Okay. Let us consider those options one by one. Let us consider this option. What is going to happen if this is true? What is going to happen if this is true? Well, first of all, if C1 is equal to 0, that means that this guy goes to 0. Okay, this is 0. So here we have the original constraint, the way it was without mixed integer variables. So this constraint will have to hold. Okay. Let me use a different marker. This constraint will have to hold because this went away. Okay. Now, on the other hand, here, this guy goes away. It is 1. So, and what we are left with is this expression that we saw before, that we said is guaranteed always hold. Okay. Right. We said it is always going to hold. So in a sense, you can say that this entire constraint goes away because it always holds. The entire constraint goes away. Okay. So the entire constraint goes away because it always holds because of how big the n is. So you can say always holds. So this is what happens. We have, this is what we call a relaxed constraint. Okay. So this constraint is relaxed. Do we have questions about this one? About what I just said so far?
Professor, can you please explain this in a graphical way, like how you are explaining, like putting the convex regions like that, please?
We have on the, I think, next slide, we have exactly what you're asking for. So in 2 slides. So let's see here.
Okay, I see.
No, I would love to explain it in the graphical way here. It's just is a little bit going to be a little bit messy, and I'm afraid I will just do the opposite and make it less clear. Zoom doesn't allow you to draw very well, so there are some problems. All right, we'll see the explanation graphically in just a bit. But let's first understand algebraically. So what happens when in this first scenario is that the first constraint becomes what it has been before we introduced the mixed integer variables. The second constraint plays no role at all in the process now. Why? Because it is relaxed. Okay, because it's relaxed. And because m is added, and m is a very big variable that makes it impossible for the constraint not to be true. Okay. Now let us consider second scenario. So let me get rid of all of this. Okay. We'll consider now a second scenario. Second scenario is this. Okay. C1 equal to 1, C2 equal to 0. Okay. What's going to happen? Well, first of all, I guess we need to understand what happens here. Here, C1 becomes 1, and we have just the same expression as we had here, right? So same expression. And this implies that this constraint will always hold, and it's going to be relaxed. So it's not going to influence X in any way. It's always holds. Because M is big, so you cannot find such X that this constraint would not hold. So X can be anything. What happens with the second constraint? Well, here C2 is 0, so this whole part goes away. And we are back at our original constraint that we saw above, like this. Becomes the same as this. So we can see that choosing C to be 1 or 0, C1 to be 1 or 0, makes you choose which region we are going to have. Is it going to be the region number 1 or the region number 2? So which one of those inequalities we are going to hold? So first inequality or the second inequality, which one has to hold? At least one has to hold. As we consider both scenarios, in each one, at least one of the inequalities has to hold. The second one doesn't have to hold, though. So it is relaxed. So this is the situation here. This is the situation. By the way, if we made it, when does inequality have to hold? When C2 is equal to 0 or C1 is equal to 0. So if C is equal to 0, inequality has to hold in this case. So if we put here bigger than 1, bigger than or equal to 1, we can add a third scenario where C1 is equal to 1, C2 is equal to 1. That would allow us to relax both inequalities. If we put here less than or equal to 1, we would add a third scenario, C1 equal to 0, C2 equal to 0, and then both inequalities would hold simultaneously. There will be additional scenario. But that does not add anything because they can hold simultaneously already. It's like no one stops them from holding simultaneously. It is just that, it is just that we don't enforce it. Okay. So this is how it works. And this is called big M method. Big M, again, stands for big constant M that you add here to relax the constraint. Now, let us see the same thing. But with a bigger problem. So now we have inequalities which look like this. We have A1x less than or equal to B1, A2x less than or equal to B2, A3x less than or equal to B3. Okay. Those are H polytopes. We can work with them exactly the same as we did before. So we create those big M relaxations. So we say a1x less equal to b1 plus m times 1. M is still a constant, so it's still scalar. 1 is a vector of ones, so it is 1, 1, 1, 1, 1. And here is we put our mixed integer variables, but notice we do it in this way: 1 minus c1. Same for all subsequent ones. It will be a2 times x less than equal to b2 plus m times 1 minus c2, a3, etc. So for each of them, we have this situation where we have constraint, original constraint. Let me box it. Original constraint plus m times 1 times 1 minus binary variable. So our binary variables have their sum has to be equal to 1. Now that is why we have this 1 minus c1 instead of times c1, because it just makes this formulation a little bit more convenient. We didn't have to do it this way. It is just how people do it in practice. So, people do it this way, so why not us too? If you think about this constraint, it leaves us with 3 possible scenarios. Before there was 2 scenarios, now there are 3 scenarios. First, C1 is equal to 1, C2 is equal to 0, C3 is equal to 0. That is the first scenario. Second scenario, C1 is equal to 0, C2 is equal to 1, C3 is equal to 0. And that's the second scenario. The third scenario, C1 is equal to 0, C2 is equal to 0, C3 is equal to 1. That is the last scenario. So let us consider all of those one by one, same as we did before. We'll just go a little bit faster. Okay. Was the first scenario, this guy. Well, if it is the first scenario, then C1 is equal to 1. C1 is equal to 1, so this whole thing is equal to 0. So this whole thing is equal to 0. So this whole thing goes away, because 1 minus 1 is 0. And we have the same original constraint. So the original constraint holds now. The original constraint holds now. Now, what happens here? C2 is equal to 0. So this whole thing is equal to 1. And we have a relaxed constraint. We have a relaxed constraint here. It is relaxed. Why do we know it is relaxed? Well, because we chose M in such a way that it would be relaxed if so a2x less than equal to b2 plus m times 1, that we choose m so big that it would always hold. This would have to be to always hold. Now, okay, what happens here? Exactly the same thing, because C3 is also equal to 0, sorry, so it is 1 here, and this whole constraint is also relaxed. So this is again relaxed, and we have one more of those things. Okay. Now, even quicker, let's consider what's going to happen with the second scenario. Well, second scenario, you can see clearly what's going on already. The second scenario, you can see clearly what's going on. Namely, that we would have here 1, okay, 1 here. Here we would have 0. 1 minus 1 is 0. So this is going away. Here we would have 1 again. So we would have one constraint which holds, one constraint which holds, this one. 2 constraints which are relaxed, this one. And that's it. Right. So we see the pattern. 0 means relaxed, 1 means holds. 0 means relaxed. And the number of C which holds is the number of region which is going to hold. Everything else is relaxed. All right. Well, last one, we'll just quickly do it. Oopsies. Okay, last one. So here we can see instantly that the first constraint is going to be relaxed because 0. Second constraint is going to be relaxed because 0. The last constraint is going to hold because 1. 1 minus 1 is 0, so this whole thing goes to 0. Right. So we have this holds together with this one, and the other two are relaxed. Okay. This is what's going on. This is what's going on. And you can see it is actually not so difficult. The process is quite simple. We just sum all the variables here and set them to 1. They are like choice variables. They choose which region is going to be active. We say active because this is the only active constraint, the only constraint that actually does anything. Those constraints don't do anything for this choice of C. If we different choice of C, another region will be active, like this one or this one. Okay. So quite interesting, quite interesting. We have a situation where we can choose a region. So we introduced OR to our programming. And that's essentially what BigM does. It introduces OR. Now let us look at it graphically. But before we do, okay, do we have questions about this? Next slide, we'll see graphics. But let's see questions about algebra. No questions. Okay. Okay. So here is a situation where we have two polytopes. Polytop number 1, polytop number 2. We call it V1, V2. Okay. Now, they represent a non-convex domain, of course. Why? As your colleague said, we can draw a line between them, and you see in between the line sticks out, so domain is not convex. Okay. How will it look with BigM relaxation? Well, if we relax the polytop V2, and we relax it as little as possible, but in such a way that any solution in the polytop V1 would also be a solution for the polytop V2. Well, this is what we are going to get. This is new boundary of the polytop V2. Okay. Original polytop V2, let me show you his boundary. Okay. So this is the original boundary. That is the expanded boundary. And why did it expand like this? Well, I chose it as small as possible so that here the furthest most edge of the polytop V1 would still be inside the expanded polytop V2. Where does this expansion come from? Well, essentially this expansion here is due to M. So big M, I chose big M in such a way that this distance is covered. Does this distance metrically equal to big M? Probably not. The reason why I say probably not is because you have to choose your big M in such a way that, how should I put it? If A is row-wise normalized, so rows of A are all equal to 1 by the Euclidean norm, then you would have your distance here to be equal to big M. But if not, then not. Okay, so that is the thing. And of course, here I chose M to be uniform. You could instead of choose just a vector of different M's, so that this distance, for example, or this distance wouldn't have to be so big. If you choose to relax in particular directions, it would have been much simpler, of course. So like this is uniform big M. So when M is just chosen the way I did it on the previous slide. But you could do it differently, of course. But you see, the point of relaxation is just to expand the boundary of the polytope, so it will subsume all other polytopes. Okay. So any x you choose would still lie inside this polytope. So let's say we choose x. Let me choose a different x here. It is still inside V2 relaxed polytope. X here, still inside V2 relaxed polytope. X here, still inside V2 relaxed polytope. But since V2 is relaxed by V1, but V1 is not relaxed, all admissible X would be inside V1. We wouldn't be able to escape V1 because it is not relaxed. V1 is still enforced. While V2 is this whole huge area, V1 is still small. So for the X to be inside both relaxed V2, V1, sorry, inside relaxed V2 and non-relaxed V1, it will have to be inside V1. Okay. That is why, by the way, I said that this is going to be slightly confusing because you can see still a little bit confusing, and definitely didn't want to draw it on Zoom. All right, now let's see the opposite case. The opposite case when we're going to expand V1. So here's V1, original boundaries of V1, and we expand them. Again, using big M. You can see we expanded them in such a way that this edge would touch. So the furthest most edge of V2 would touch V1, a relaxed edge. That is the smallest possible big M, which would satisfy us. Because again, we use the scalar big M. We could have used, we use the same big M on the whole H representation of the polytope. If we used a separate big M for each half space, we could have done more economic expansion. But here I used one big M for all edges. Right, so now you can see any solution would have to be inside V2. Why? Because any solution has to be inside V2. V2 is not expanded, but any solution inside V2 would also be inside the relaxed V1. So whereas here the solutions were inside V1 always, because V2 was relaxed, here on the contrary, it is all solutions are inside V2 because V1 is relaxed. So this is how geometrically it looks like with big M. This is how geometrically it looks like with big M. Do you have questions? Do you have questions about this geometry, for example? Well, I understand that it's a little bit difficult. So I'll upload this on the internet, so we'll be able to kind of like go over this part, or you can just look at the slides. I think that might be just as easy. But I understand that you're not going to get it from the like one iteration. Like for me, it took way more than one iteration to understand the concept, and I had to work through it with a piece of paper too. So it's okay. Now, what do we do when we have multiple variables? That is our path planning problem. Remember, it included multiple variables: k, x1, x2, x3, x4, etc. And we were only talking about one variable. So each of those variables can make a choice independently. Okay. So each of those variables doesn't have to choose the same polynomial as the previous one. Like x1 can choose the polynomial number 2. X2 can choose polynomial number 2. X3 can choose polynomial number 1. X4 can choose polynomial number 2 again, and so on, right? They can choose whatever. So how do we implement it? We'll implement it this way. We still do the same thing as before, produce relaxed, big M such a way that those constraints would be relaxed if decision variable here turns into 1. So 1 minus 1 will be, it turns into 0. If it is 0, it will be relaxed. If it is 1, it's not relaxed. Okay, so this is the same. We use exactly the same formulation y minus c here. So y minus c doesn't change. And we even have the same like coefficients here. Okay, just additional k here. Okay, and notice that we still have the same sum here. Equal to 1. Same stuff here. So the only thing that changed is this additional k. Let me show you. So this k means that we have not just one set of decision, like those switching variables, so choice variables, right? C, but we have k sets of those variables. So we have C1, C2, C3, one set for the x1, another set for x2, another set for x3, another set for x4, and so on. So this k corresponds to this k, okay? It corresponds to this k. And for each of them, we have this separate inequality here. So this whole inequality would have to hold for each of the x's individually. So for each x, this inequality holds. So you don't have any longer one equality, one equality where you have C1 plus C2 plus C3 equal to 1. You have k of those inequalities, or I don't know how many, like big k equalities. Okay. Each of them has to have to hold independently. And each of them produces a 3 scenario as before. And those 3 scenarios govern how each particular x will choose the region. Okay. So the number of decision variables, binary decision variables, is 3 times big K. Okay, and that is how you do. That is how you do your. How should I put it? That's how you do your mixed integer here. Of course, we could make it like maybe easier to understand if we chose, for example, to call it like alpha, beta, gamma. Let's say alpha plus beta plus gamma is equal to 1, something like this. And then it will be like alpha k, beta k, gamma k, etc. So we could make it simpler in terms of naming. But ultimately, I think this is all quite simple. This is all quite simple. Okay. So this is mixed integer. And this is extremely useful. You can use this for path planning. You can use it for design. I'm not going to show you here, but we have been using this, for example, to design topologies of tensegrity structures. So you can do that. Anytime you have choices, discrete choices to make, you can try to use mixed integer. Yeah, people used it for planning footsteps and body orientations of walking robots. People use it for like more or less anything. Well, this is one of those extremely useful things. And in your choice of work, there is a big chance that you would still find some problems that haven't been solved that can be solved with this algorithm. So I recommend you trying to learn this. Extremely useful. All right, we I think almost out of time, so I will just hurry up a little bit. So now the problem of path planning with big M relaxation looks like this. So again, the minimal distance first has to be at the start, last step has to be at the goal. We have additional decision variables, binary decision variables here. Okay, binary decision variables. Let me denote it as I was doing the whole thing as a blue. Binary decision variables. And now we have our big M relaxation here. we have our decision variables exactly as in the previous example. It's just that I now determines which region we step to. I is the number of the region. K is the number of the step. Okay, so K is the number of the step. Okay. The sum over i's, notice the sum over i's. So I is a region. I is a region. Okay. The sum over i's will be equal to 1. So the sum over regions, not over steps. Okay. And that's it. So this very simple program where we have big M relaxation. We have binaries, sum all regions to choice variables for all regions have to sum to 1. That's it. Like, I mean, simple. It's simple. And this is all we need to do to plan footstep, plan, or discrete path, whatever you want to call it, from point A to point B on a non-convex set. So on the set of on the union of convex sets. Okay, over the union of convex sets. And that's it. That's it. That's it. Yeah. So this is how we can plan it. Now, what I was saying before, it was you should probably add this component here. Otherwise, your steps would all stay at the start. It's not even going to plan any path. It will just place all the steps at the start. So you have to add this cost, which forces the program to mostly put the steps close to each other. By the way, you can also strike down those. And then you would have what you would minimize the actual distances between steps. With the squares, if you put squares here, what's going to happen is a step like this would be equivalent to one step like this. In terms of the squares of the square of this step is equal to the square of those two steps. And the last step can be 0. So it's like, you have to be careful because with squares, you have Pythagorean theorem. So you can, I mean, ideally, what we would prefer is something like 2 steps here, like 1 step, 2nd step. That's what we would prefer. Okay. But we definitely don't want this to happen. Okay. In terms of the sum of the norms, this guy is equivalent to so this guy will be bigger than either this or this. But in terms of the so how should I put it? Like this can happen because those two are the same in terms of the squares. Okay, sum of squares, they're the same. Okay. Now this can happen because those two are the same in terms of the norms. I have to be careful in both cases. But anyway, you have to tweak your cost function in such a way that the path that you produce is meaningful. But that is usually, we always have to tweak our cost functions. So this is just normal. Okay. So this part is just for uniformity of the steps. Otherwise, all your steps will be at the start. Because why not? Okay. Now, this is how you can code it. The slides contain a code example. This is just me generating random regions. I shift them. find convex hull, turn it into H representation, all this in MATLAB. Number of steps that we want to plan, starting point, finishing point. Here it is at the center of the first polytope, finish at the center of the last polytope. Weight in the cost function, big M 15, and then I do it in CVX. You can see I provide a variable, continuous variable, binary variable C. Now we have a cost, which is the sum of the norms of the sequential steps. That is what I was pointing out in the last slide, plus the stack point cost times weight times the first. So the starting point, the distance to the starting point, the distance to the goal for the last step. Okay, we minimize the cost. Next, we do our mixed integer constraints, which you can see are very simple. We do a for. You say this is our original H polytope. This is our relaxation. You see it is almost exactly as I was writing on the slides. And we have this additional equality constraint. That's it. It's going to solve. And then you just plot. Of course, the plotting you can do much better, but that is just to make it simple. All right. So this is how we do it. This is how we do it. Now, last thing before we leave, I was thinking of maybe showing you a little bit more. Yeah, I was thinking of maybe showing you a little bit more. So you can decide, you can let me know maybe in the chat after the class if you want to see more of mixed integer on it. For example, we could discuss how to solve Sudoku puzzle using mixed integer automatically in as an optimization program. It's not because anyone likes Sudoku, maybe we will like Sudoku, it's okay, no judgment. It is because it is something that you don't think is easy to solve as a convex optimization. And it is easy. So we can discuss how to do that. All right. So yeah, we can discuss it in the next beginning of the next lecture if you want to. But if not, we can skip. It's fine. I don't want to give you something that's not exciting. You know, all I want is for you to kind of get to like mixed integer. But okay, before we go, let me just show one last thing. I showed you how to relax inequality constraints. So those were inequality constraints, remember, that we relaxed. Sometimes you want to relax equality constraints. For example, let's say your control input is equal to either BU, B1, U1, or B2, U2. It is equal to either one or another, okay? It cannot be equal to both of them at the same time. For example, you have one set of thrusters and another set of thrusters, or you have one control policy and another control policy, and you have to choose either one or another. You cannot choose both. So you can also do it as a mixed integer program, and the way it is done is using norm. So you to relax equality constraint, you normalize like this. You'd say, okay, B1 times U1 has to be less than or equal to big M times 1 minus C1. B2 U2 has to be less than or equal to this guy. Why does it relax? Well, because if M is big and C1 is equal to 0, this is just a big number. So this doesn't constrain you to anything. It just says that U1 has to be inside some huge ellipsoid. It doesn't matter. But if C1 is equal to 1, then this guy is equal to 0. This whole thing is equal to 0. And the only U1 that would produce 0 here would be 0 U1. Well, if B has like a null space, then U1 will be in the null space of B. But that is the same thing because ultimately the part here will still be equal to 0. So that is the whole point. So this variable will become 0 if C is equal to 1. And since we do this, one of them would have to be set to 0, and another one can be anything. So, and this is how you can relax this type of situation. For general equality constraint, let's say you want equality constraint of this type. Ax equal to y. You want this equality constraint to be relaxed. How do you relax it? Well, you do it this way. Ax minus y less than or equal to m times 1 minus c. And if you want, like, if you have n of those constraints, you have, like here you would have, for example, I. Okay. So this is how you relax equality constraint like this. So the trick is to use norm instead of adding something to inequality constraint as we did before. You just do a norm. Essentially, this is the same thing as before, because linear inequalities, you can see them as just simplified case of a norm, I guess. Kinda, not really, but kinda. Because H polytopes represent a bunch of individual inequality constraints. So we were just abusing our power, relaxing all of them at once. That is the whole point of what we were doing. Here we turn a bunch of equality constraints into one with a norm function. We could do it line by line too. But here, I don't know if it makes sense. Yeah. So this is the situation here. This is how you can relax equalities. And so this is a way, for example, where you can choose between two control laws. Let's say you have two controllers, u equal to k1x or u equal to k2x. How can you choose between the two? You can choose it this way too. So anytime you have a choice, you can do it with decision variables of this type. Right, we're definitely out of time, I believe. So this is it for the class. Do you have questions? Right, if we don't, then let me thank you for listening. Next time, on a Thursday, you can come with questions. Let me know in the chat if you want me to discuss more on mixed integer. Definitely one of the most useful topics out there. Yeah, so we can look at more examples a little bit. Otherwise, we already have our next topic, so it is okay. We can move on, with the program. So just let me know what you would prefer. We'll see you then. Bye-bye.
Thank you, Professor.
Thank you.
Bye.
Bye.